Ever wondered what would happen if you tried to text your friend while getting sucked into a black hole? It might be the last text you'd ever send. Why? Because black holes bend space and time so severely that not even light can escape its gravitational well. Welcome to part 2 of our 3-part miniseries, where we'll dive headfirst into the strange and wacky world of black holes, talking about how they form, what happens when you jump into one, and how they evaporate. Yes, they evaporate. So stay tuned until the end of the video to learn more. To recap, in part 1, we explored how stars form from giant hydrogen clouds called nebula, then spend most of their lives fusing hydrogen into helium, starting as protostars. From there, stars that fail go into fusion or only produce fusion for a short period of time are turned into brown dwarfs. Smaller stars, like our sun, end as white dwarfs supported by electron degeneracy pressure, while bigger stars can go supernova, leaving behind neutron stars, or if massive enough at death, above 3 solar masses, they form black holes. 1 solar mass is the mass of our sun, roughly 2 times 10 to the 30th kilograms. So with that framing, let's see what happens when a star is just too hefty to keep itself together. A black hole is a super dense star whose gravity warps space-time so intensely that even light traveling at 186,000 miles per second cannot escape. Imagine a trampoline with a bowling ball on it. Clearly, the trampoline curves under the weight. A black hole is like a bowling ball so heavy that it tears through the fabric, creating an inescapable pit. The boundary of no return is called the event horizon, determined by the Schwarzschild radius. For our sun, which has a radius of around 433,000 miles, it would need to collapse its mass into a 2-mile radius to turn into a black hole. For the Earth, which weighs around 6 times 10 to the 24th kilograms and has a radius of 6,300 kilometers, it would need to have a radius of around 1 centimeter, the size of your fingernail, to turn into a black hole. So thankfully, none of that is happening. When a massive star's core collapses, it crushes matter into a volume so small that classical physics breaks down. Some theories suggest that the reverse of the Big Bang occurs when a singularity forms. The star becomes opaque as light has no room to move, forcing particles to recombine into a sort of primordial soup with reverse symmetry breaking, until at Planck scales, a singularity forms, an infinitesimal point of infinite density. Stephen Hawking, the physicist, once said, "The singularity is outside the scope of presently known laws. We simply don't know what happens there." Even though the singularity itself is hidden from our view, black holes can reveal their presence through their gravitational influence on the surrounding space. They can even grow in anticipation of incoming mass. Renowned physicist Kip Thorne once pointed out, when matter falls into a black hole, the absolute horizon starts to grow, effect, before the matter reaches, cause. The horizon grows in anticipation that the matter will soon be swallowed and will increase the hole's gravitational pull. If that's not freaky, then I don't know what is. Because black holes emit no light, we detect them indirectly by tracking their effects on nearby stars, gas, and accretion disks, which are swirling rings of infalling matter that often emit intense X-rays. As matter falls into a massive star's collapsed core, any angular momentum transfers to the black hole, creating a spinning or Kerr black hole, named after basketball legend Steve Kerr. I mean, famous physicist Roy Kerr. Most black holes spin and create an ergosphere, which is an area just outside the event horizon where space-time is dragged around. Think of it like you're stepping on a fast merry-go-round. You're forced to move around with it. That said, you're not completely trapped yet. You can still move in and out of the ergosphere. Furthermore, unlike a regular black hole, spinning black holes can develop 2 event horizons. The outer one is the usual boundary beyond which light cannot escape. The inner horizon behaves far more strangely. In theory, it allows for closed timelike world lines, meaning you could travel into the future and somehow loop back, meeting yourself in the past. Physicist John Kerr calls these bizarre spacetimes, and while the math suggests they're possible, real-world conditions may prevent such exotic loops from actually forming. And at the center of a spinning black hole lies the ring singularity, which remains a mystery. Now, let's see what actually happens if you fall into the black hole. Let's bring back our 2 friends, Joe and Misty. They're both on a star which is about to collapse into a black hole. But Misty decides to stay at a safe distance away while Joe is feeling adventurous and decides to stay up close and personal. At first, everything seems normal. Joe texts Misty updates like, "I'm at 2 seconds, 3, so on and so forth." But at 16, the star starts to collapse. Joe's elapsed time is now moving slower relative to Misty's. If he experiences 16 seconds, then she experiences more than 16 seconds. As the star compresses past its Schwarzschild radius, Joe appears to freeze near the actual horizon. Once the black hole forms, his signal of 16 seconds gets stuck, never actually reaching Misty. In fact, Misty never sees Joe cross the black hole. He just gets endlessly redshifting, approaching a faint signal that really never reaches the final timestamp. Meanwhile, Joe experiences intense gravitational forces. He gets stretched in one direction, squashed in the other, and is basically just pulled in all directions in a process called the spaghettification. If he continues inward, perhaps some quantum gravity mystery takes over, but no one really knows what happens inside the singularity. Again, it's outside the presently known laws. Surprisingly, some solutions predict that you may skip the singularity altogether.
So you're telling me there's a chance?
But the conditions have to be just right, like having exotic matter with negative pressure density, or charge density must outweigh mass density. In those rare scenarios, wormholes could form, bridging two separate points in the same space-time or two different spacetimes altogether. Think of wormholes like cosmic shortcuts. You enter on one side and reappear somewhere else, potentially without being crushed, right? That'd be kind of fun. But these exotic requirements like negative pressure density are not exactly things you would find at your local Whole Foods. For now, wormholes remain tantalizing theoretical playthings. The last crazy thing about black holes is that they evaporate, albeit on a very long time scale. Enter Hawking radiation. Near the event horizon, quantum mechanics says that virtual particle-antiparticle pairs pop in and out of existence together. Immense gravitational forces can yank these particle pairs apart, with one falls into the black hole and the other falls out. Under E equals mc squared, we see that the particle that falls into the black hole has negative energy and reduces the black hole's total mass, leading the black hole to slowly lose mass over time or evaporating. This process takes eons, on the order of 10 to the 67 years, which is roughly 10 to the 56 times longer than our current universe's lifespan of 13.8 billion years. As the black hole shrinks, it heats up, radiating energy faster and faster until poof! It may explode into one final high energy burst. So, from stars collapsing into gravity wells so deep light can't escape, to wild speculations about time loops and wormholes, black holes remain some of the most mind-bending objects in the universe. They challenge our understanding of physics, pushing us towards new frontiers. If you enjoyed this cosmic adventure, then make sure to like, subscribe, and hit that notification bell so you won't miss out the final part where we talk about galaxies. So until then, I'm gonna be eating a cookie. Adios, bye, deuces, boop.